All right, problem one says find a parameterization for each surface described below. Be sure to include the domain for your parameterization. And in part A, we have the cylinder x squared plus z squared is equal to 4, where y varies from 0 to 3. So this is really similar to what we just saw in the last video where we parameterized cylinders of the form x squared plus y squared is equal to some constant squared. But now z and y are just swapping roles. Okay, so we can approach this in much the same way. We'll use a modified form of cylindrical coordinates where I'm going to swap the roles of y and z. So now y is just itself and z is r sine theta. X is still r cos theta. And note here that the polar distance r now, which is really describing the distance from the y-axis, this is the square root of x squared plus z squared. And so on the cylinder, r is just constant 2. And so if we set u equal to theta and v equal to y, then these equations here will give us these components for our parameterization. And for the I component, we'll get 2 cosine u. For the j component, that's just going to be v because v is equal to y. And then for the k component, we'll get 2 sine u. And u here will vary from 0 to 2 pi. And v, which is just y, that's going to vary from 0 to 3. All right, not too bad. So let's look at part B. Well, this one's immediate. This is the sphere of radius 3 centered at the origin. And in the last video, we parameterized spheres of radius a centered at the origin. So all we have to do is set a equal to 3 in that parameterization, and that's going to give us 3 sine u cos v, and then 3 sine u sine v, and then 3 cosine u. And u here, which is just phi in spherical coordinates, that's going to vary from 0 to pi. And v, which is theta, that's going to vary from 0 to 2 pi. Okay, it's not bad. How about part C? This is a parabolic cylinder. Y is equal to x squared, and z varies from 1 to 4. So here's a picture of that cylinder. And the thing to note here is that any point on the cylinder, okay, can be represented with coordinates of the form x comma y, but y is x squared, and z being independent of both x and y can take on any value it wants from 1 to 4. So if I set u equal to x and v equal to z, I get the parameterization u comma u squared comma v, where u, just being x, can take on any value it likes, and v, being z, it's bounded from 1 to 4. All right, cool. Let's look at D. We have the plane 3x minus 4y minus z is equal to 2, and the points x, y are going to vary over this rectangle. And here, the thing to notice is that we can easily solve for z. So we really have a explicit surface here. Z is 3x minus 4y minus 2. So as we discussed in the last video, I can immediately write down a parameterization then of the form x comma y comma z, and I just punch in this expression for z for the k component. And then here x varies from -2 to 3, and y varies from 0 to 4. All right, cool. So now let's go ahead and make a little space for the last problem, which is E. This is the cone z is equal to h over a times the square root of x squared plus y squared. And here z varies from 0 to h. So first note that the height of this cone is h because we're letting z vary from 0 to h. And if I look at the circle here at the top, okay, this has radius a. And the reason why is that if I set z equal to h, okay, the h's are going to drop out, and I get that the square root of x squared plus y squared is equal to a, implying that this circle here has radius a. All right, so now let's go ahead and write down a parameterization. So first thing, note that on the cone, okay, z is equal to h over a times the, well, square root of x squared plus y squared, but that's just r in cylindrical coordinates. So z is h over a r, or put another way, r is a over h times z. Okay, so here are the cylindrical coordinates. And what we're going to do, just as we did in the last video when we parameterized cones, we're going to set u equal to theta and v equal to z. Oh, sorry, I need to get rid of this stuff down here. It's getting in the way. And also just to remind yourself that, okay, if I set v to z, okay, and I also know that r is equal to a over h times z, then r is a over h times v, right? And so now punching all that stuff in here, we'll get x is equal to, well, r, which is a over h times v, times the cosine of theta, and u is theta, so we just get the cosine of u. And then for y, we'll get r, which is a over h times v, times the sine of theta, which is just going to give us the sine of u. And then lastly, z is just itself, and we're setting z equal to v, so we get just v for the k component. And here u varies from 0 to 2 pi, and v, just being z, varies from 0 to h. All right, that is going to do it. Thanks so much.